Good evening, everyone, and welcome to the second webinar in our Smart Wastewater Treatment Plants series. The series, which is presented through a collaboration between the Smart Sustainability for Water and Energy Company and Aqua Energy Expo, as part of a shared action to promote practical knowledge exchange and highlight innovative technologies that enhance energy efficiency, operational reliability, and sustainability in wastewater treatment plants. We're pleased to have you with us today for a technical session titled The Next Generation of Air Blowers Delivers the Ultimate Equation in Wastewater Treatment Plants Performance. Today's webinar will focus on advanced air blower technologies and how next generation blowers are enabling wastewater treatment plants to achieve higher energy efficiency, better oxygen delivery, fewer breakdowns, and lower operating costs. A key topic we'll address today is how modern blower control philosophies go beyond the conventional single-point VFD control and how advanced concepts such as the combination of lead guide vanes and variable diffuser vanes allow blowers to precisely match fluctuation process demands while maintaining high efficiency across a wide turn-down range. It's my pleasure to introduce our speaker for today's webinar, Mr. Florian Adam, member of the Broad and Sales Director at Next Turbo Technologies. Throughout today's session, Mr. Adam will share a real-world insights, comparative assessments of blower technologies, and reference projects from some of the world's largest wastewater treatment plants. Before we begin the main technical presentation, we'll start with a short opening introduction by Dr. Mehal Hamoud, Business Development Director for the Middle East at Bender Group. He'll set the framework for today's discussion. We'd like to inform you that obtaining a certificate of attendance requires registering the data through the form sent in the chat box during the webinar. مساء الخير على حضراتكم جميعا. أهلا بكم في الويبنر الثاني من سلسلة محطات معالجة الصرف الصحي الذكية، واللي بيتم تقديمها بالتعاون بين شركة الاستدامة الذكية للمياه والطاقة ومنصة أكوا إنرجي ضمن مبادرة مشتركة هدفها تبادل الخبرات والمعرفة العملية وتسليط الضوء على أحدث الحلول والتكنولوجيا اللي بتساعد على رفع كفاءة الأداء، تقليل استهلاك الطاقة وتعزيز الاستدامة في محطات معالجة الصرف الصحي. يسعدنا وجودكم معنا النهاردة في جلسة فنية بعنوان الجيل الجديد من نوافخ الهواء Air Blowers يحقق المعادلة المثالية لرفع كفاءة الأداء في محطات معالجة الصرف الصحي. الويبينار النهارده بيركز على تكنولوجيا الاير بلاورز المتقدمه وازاي الجيل الجديد من البلاورز بيساعد محطات معالجه الصرف الصحي على تحقيق كفاءه اعلى، نقل اكسجين افضل، اعطال اقل، وتكلفه تشغيل اقل على المدى الطويل. ومن المحاور المهمة اللي هنتناولها النهاردة هو تطور فلسفة التحكم في الإير بلاورز والانتقال من الاعتماد على التحكم التقليدي باستخدام ال VFD لمفاهيم تحكم أكثر تطور زي الدمج بين ال LED Guide Vanes وال Variable Diffuser Vanes، واللي بيسمح للبلاورز إنها تواكب تغير الأحمال التشغيلية بدقة عالية مع الحفاظ طبعا على كفاءة مرتفعة على مدى واسع من معدلات التشغيل. يشرفنا النهاردة أننا نقدم المتحدث في هذا الويبينار مستر فلوريان آدم، عضو مجلس الإدارة ومدير المبيعات في شركة نيكست توربو تكنولوجيز. خلال الويبينار هيشاركنا مستر فلوريان رؤى عملية من أرض الواقع ومقارنات بين تكنولوجيا البلاورز المختلفة، بالإضافة إلى أمثلة من مشاريع مرجعية في أكبر محطات معالجة الصرف الصحي في العالم. قبل ما نبدأ حابين ننوه على حضراتكم بتسجيل البيانات في الفورم المرسلة في الشات بوكس خلال الويبينار للحصول على شهادة الحضور. هنبدأ بكلمة تمهيدية هيقدمها دكتور ماهر الحمود، مدير تطوير الأعمال لمنطقة الشرق الأوسط في مجموعة بندر، واللي هيحط الإطار العام لموضوع الويبينار. اتفضل دكتور ماهر، مايك is yours.
السلام عليكم ورحمة الله وبركاته. وأنا حقيقة I would start just only in Arabic and then we will change to English. First of all أول شيء أشكركم جميعا على هذه السلسلة الرائعة، السادة المشغلين إلها في سمارت سستينابيليتي وأكوا إنرجي إكسبو. إحنا شرفنا اليوم راح كما يقال هي المتعة والإفادة وخلينا نقول المعرفة مضمونة 100%. أنا متأكد أفضل خبراء العالم موجودين في معالجة مياه الصرف الصحي بالتحديد، وراح نكون أكيد سابقا زي ما مثلا بالسيشن الماضي مع السيدة مانويلا كيف الانتجريتد سوليوشن والبيست بلورز هو أهم ما العناصر الموجودة في المعالجة بشكل عام والإيريشن بشكل خاص. I will change to English. It's an honor to be part of sustainability series at sewage treatment plant, and to introduce Mr. Florian Adam, one of the world's of experts in blowers technologies, maybe the most best who can talk in these topics. And enjoyment is guaranteed 100%, and the knowledge will be valuable. I know. For now, I hand the microphone over to Mr. Florian, and we will join in the end of this session. Thank you very much for all.
Thank you very much, Dr. Maher, for the introduction and for setting the context for today's webinar. At this point, we'll move forward with the technical part of the session, where we'll explore modern air blower technologies, performance optimization strategies, and practical applications in wastewater treatment plants. We'd like to remind you once again that obtaining a certificate of attendance requires registering the data through the form set in the chat box during the webinar. Mr. Florian, you can go ahead. Mr. Florian, can you hear me? Your mic is muted. We can't hear you.
Mr. Florian, we don't hear you up to now. I feel like this is muted. Noch nicht. Noch nicht. Nein.
Mr. Florian, we only can see your screen, but we can't hear your voice. You can activate the mic.
He's trying. No issue.
We can see your mouse moving, but we can't hear you.
If there is, take your time. It's I think it's a whole.
Can you hear me now?
Yes. Nice. Perfect. Take your time.
Thank you very much. Thank you. You can see my screen?
Yes.
Very good. Thank you. Welcome to this open webinar, now that we have solved the technical problems. Thank you also from my side to Aqua Energy Expo and Smart Sustainability for organizing this forum. And before we start, I would like to introduce myself a little bit. My name is Florian Adam. I'm active since more than 18 years with blowers and compressors, mainly in the wastewater treatment industry, but also in other industrial applications. In my professional life, I had the chance of working with several industry leaders in this aspect, from Siemens, Demag, HV Turbo, and now with Next Turbo. If I have met some of you already in my professional life, then please give me a shout later on or on LinkedIn if we don't have the time in this forum. Before we go into the topic of the day, the next generation of air blowers for the aeration in wastewater treatment, I would like to give some visual impressions about the company Nexturbo, so that you know a little bit with whom you are talking here and have a little bit of a better feeling. We are located in northern Italy. The company was founded by a group of industry veterans that you can see on the left lower page. The idea was to address the shortfalls of the existing blower packages in the market. In this mission, we have been quite successful so far. More and more clients around the world are changing their approach to specifying blowers, buying blowers, and operating blowers. And this is what I wanted to talk today about. You can see some photos of our production, some semi-finished blowers, so that you get a little bit of a hands-on feeling how the final product that I'm talking about here today is looking. Some installation, from large-scale installation to smaller plug-and-play blowers, you can see in this slide. In the Middle East and the Gulf region, and that is, of course, also the focus of today's webinar, the selection of the right blower type and brand is maybe of even more importance than in other areas of this world, mainly due to the challenging climate and the surroundings that your plants are operating in. A wrong choice will quickly be visible in breakdowns, in downtimes, and in worst case of replacement of blower equipment. This is why in the Middle East, in the region, mid and large scale wastewater treatment plants have all selected Nexturbo for their blower of choice. We can see plants like Jebel Ali in Dubai, Vassan, another one of the two big wastewater treatment plants in Dubai, where the recent project with Al-Kharafi, MAC, and Veolia is in the finalization process. All their Nexturbo blowers have been installed. Al Hayman in Kuwait, Tubli in Bahrain, and many smaller ones have chosen this technology that I'm talking about today. Now, from now onwards, to demonstrate the advantages of the Nexturbo blowers, you have to understand the background of blower operation, how blowers work. In order to do so, I will dive a little bit in how blowers are constructed, but I will also show the field of different blower types. We will work out today an ideal blower, the best-in-class blower, how something like that would look like, and then we will compare Nexturbo against it. No? So by defining this ideal blower, we have a measure to judge not just Nexturbo blowers, but in your professional life, when you get quotations on your desk of other blower manufacturers or blower types, you will have that ideal to compare them against. So here you can see the field of blowers, air blowers that are used in wastewater treatment plants, specifically in aeration process. Low pressure blower. On the left side, you can see the known volumetric machines, which is positive displacement blowers. They're also called roots blowers or lobe blowers, and the screw blowers. The defining characteristic of those blowers is that they trap air in a segregated volume and then move it onto the pressure side. So they are essentially air pumps. That's the working principle of this type of blower. They are usually utilized in smaller applications, very small treatment plants, 50 kilowatt or around. The capex is cheap. They're simple machines. But of course, if you go bigger, then efficiency becomes more and more a criteria to look after. And then, of course, treatment plants move more to the centrifugal type that you can see here on the right side. The centrifugal type is split in two large segments. There is the multi-stage, where you compress the air over multiple stages, as the name implies, and single stage. The multi-stage blower for wastewater treatment is a little bit on the phasing out of the wastewater market. It has started a decade ago in 50 hertz countries. They have been still in the market in 60 hertz countries, simply due to the fact that the motor turns quicker in 60 hertz, which gives them a little advantage. But also there, they are phased out, mainly due to the fact that the efficiency is only on the mid-range. In modern wastewater treatment plants, the blower that is being utilized is a single-stage centrifugal machine, and there you have two distinct types, the speed-regulated machines and the variable vane machines. And we will focus us on those two types today and compare them against this ideal blower. Now, these single-stage centrifugal blowers, you can split among several dimensions. The configuration of those blowers is what counts. You can split them along how the airflow is being regulated. Aeration blowers in wastewater treatment plants need to be able to regulate the airflow, not just 100%, but also part load. And you can do that, as you can see on the left side, you can do this with modulating vanes. You can see that with modulating vanes, or you can do that with a speed regulation. Another differentiation is how you increase the impeller speed that is required to increase the speed of the air. That is the fundamental principle of how you compress air in a centrifugal blower, that you increase the airspeed. And there are two different ways of doing that. You can do that with a high frequency, 800 hertz, for example, VFD. It's a specialized VFD that makes the motor turn at the required 10 to 40,000 RPM. Or you can do that with gears, where you utilize 3,000 RPM, 2-pole or 4-pole motors, and then you go in with a gear ratio of 1:6 or 1:8. The third criteria is the bearing type. You can use oil bearings, which is ceramic bearings or hydrodynamic bearings, or you can use magnetic or airfoil bearings. And we will discuss all these different configurations in this presentation. Motor type, I already mentioned it. There's two different. There's a standard 2-pole, 4-pole motors, the asynchronous type that you can buy from Siemens, ABB, WEC, and 100 other brands. And then there's the synchronous permanent magnet motor type. If you choose one of those configurations, then automatically the rest is being determined. The rest makes the most sense then together in a package. So two distinct types of blowers you can see here along the line that is splitting these criteria. And that is the integrally geared modulating vane blower and the so-called direct drive blower. You know them maybe under different names. You know them under turbos, high-speed blowers, permanent magnet blowers, maglev, which means magnetic bearing blowers, airfoil blowers. So they are just different names for the same type. So those two types you can see over the different configurations we're focusing on. Next Turbo supplies both types, the integrally geared modulating vane blower and the magnetic bearing blower. And I don't want to spoil the result of the presentation here, but I just wanted to highlight that Next Turbo is not actively promoting and selling their magnetic bearing blower in the Middle East. The reason is, as I mentioned, the challenging climate that is prevailing in the Middle East, especially in the Gulf region, which has severe disadvantages for the magnetic bearing blowers, and it doesn't live up to the operational reliability that we are offering to the client. So in the Middle East, we're focusing ourselves on promoting the integrally geared modulating vane blower. This is the product portfolio of Next Turbo. You can see different sizes. You can see different packages at the bottom. You can see our GTB, which is an oil bearing, ceramic bearing line. You can see the GTH line, and you can see the magnetic bearing line. But I'm not going into detail on this product portfolio. I want to explain the distinguishing between these types. And by doing so, I will go through these comparison criteria. The two different types I will compare alongside these criteria against that blower ideal. Lifetime, efficiency, regulation range, maintenance, quality, and of course price. Not just CapEx, but life cycle cost. And those are also the criteria that you should use whenever you face a blower quotation or a blower product in the market, and you need to evaluate its quality. Now, the comparison in efficiency. In my eyes, the most important criteria is the efficiency. It of course depends on project by project. If this is the most important one, if you talk with an end client, it surely is. He needs to settle the energy bill. If you talk with contractors that have 10 or 20 years operation of the plant in their business, then of course it is also one of the most important aspects. So, let us design here and now today a centrifugal single-stage blower. As I mentioned, the aim of a blower is to increase the airspeed. So you have air entering the rotating impeller, and then by centrifugal force, you increase the airspeed. You do that by turning the shaft and turning the impeller at a certain speed. The way you are choosing the geometry of the impeller, the curving, the dimension.
Mr. Florian? Mr.
Yes.
Florian?
Yes.
Sorry for interrupting you, but we can't see the screen sharing.
Understood. Just now or the whole time?
No, just now.
Okay. Let me see where the issue is. Can you see it now? Yes.
Yes, it's okay now.
Perfect. So, as I said, we are designing a centrifugal single-stage blower. You have the air entering the impeller, and by centrifugal force, you're increasing the airspeed. That's the way you are compressing air. By turning the shaft at a certain speed, you define the compressor curve, how the curve is reacting, depending on system pressure, by designing a certain geometry of the impeller. How the impeller blade is shaped, how the impeller's dimension are chosen. In a wastewater treatment plant, you have a certain water column in the basin that you need to work against. It's a certain system pressure that you need to work against. So you are defining this system pressure, plus some dynamic losses, of course, in the pipe, as your design pressure, the blue point. That's your requirement. You require a certain amount of airflow at a certain amount of pressure. And that's how you design your impeller and your speed, so that you end up with this compressor curve. Now, of course, you cannot just have a blower which runs only at 100% airflow. You need to be able to regulate the airflow of the compressor, namely to reduce the airflow. We can do that, as indicated here, in a simple way by just putting a VFD to the motor and reducing the motor speed, and therefore reducing the impeller speed. The effect on the curve is that your performance curves will move to the left, which means less airflow, but it will also drop in pressure. And the relationship is that if you reduce the speed, your airflow goes linearly down, but the ability of the compressor to work against pressure drops to the power of 2. It drops exponentially. Now, why does that happen? You might know simple water pumps, centrifugal pumps. If you use a VFD on a pump, it gives you a good result. It gives you an energy-saving result. Why? Because water is a non-compressible medium. But here we are talking about air blowers. Air is a compressible medium. And that's why you get this pressure drop, this negative pressure drop, if you put a VFD on a centrifugal air blower. Now, imagine we need still less air, and we're reducing the speed with the VFD even further. You can see that the curves move further down, but the problem is we can only use these first 3 speed curves. We cannot use the last speed curve because it is under the water column pressure, which means the blower cannot work against the water column. It cannot work against the system pressure. The blower will go into surge. It will violently shake, and go into surge. So we cannot use this speed curve. So your regulation range is defined by this range, by this blue line. Now, the problem is that in a centrifugal blower, the best efficiency point is always on the top of the curve, close to surge. Now, you are operating alongside this blue line at this constant water column, which means you operate in a very bad efficiency, and then it gets gradually better if you turn down. That's, of course, not what we want. We want a more efficient blower. So let us see, what about if we design the impeller and the speed so that our required airflow and pressure is in the most optimum range, in the green efficiency range. If we then reduce the speed, you can see that we suddenly cannot use the speed curve number 2, number 3, and number 4, because they're under the system pressure. So we have increased the efficiency of the blower, but at the same time, we have decreased the regulation range, the airflow range the blower can work in. And that is the trade-off of a speed-controlled blower with a VFD. If you put a VFD on a blower, you have to make a trade-off between efficiency and airflow regulation. You cannot have both. Typically, this type of blower operates 75% to 100% of airflow. Now, let us see if we can design a better blower where we don't address this shortfall. So let us start from the same starting point, but this time we are leaving the speed of the impeller constant. We are putting variable diffuser vanes on the discharge side of the impeller. When we change the angle of those diffusers, we are changing the relative airspeed at the discharge side of the impeller. What happens if we change the angle, if we reduce the angle a little bit, the compressor curve is moving only to the left. We are not having this drop in pressure, this unwanted drop in pressure. So let's plot it over the whole position range of those diffusers, and then you will get a regulation range that you can see is very wide, 40 to 100% of airflow regulation at a constant pressure. And if we look again at the efficiency range, best efficiency is on top of the curve, you see that we are always operating at the highest efficiency. So now you have designed a modulating vane blower. It is efficient and it has a wide turn down range, airflow regulation range. But let's see if we can further improve this design. Imagine it is night. We have a drop in temperature, or your process, your wastewater treatment plant process requires less pressure. What will happen is suddenly you're operating in this point at a lower pressure point. You will be in the yellow range of efficiency. What we do is we leave the variable diffuser vanes and we add inlet guide vanes in front of the blower, in front of the impeller. By doing that, we are basically pre-rotating the air that enters the blower. And the effect on the performance curve is that you're moving all those diffuser position curves down and to the left. So suddenly you have a mechanism so that during night, where the blower runs suboptimal, you can move the whole performance envelope and be again in the most efficient area. If you have pressure drops in your process, less water column, you can do the same. You can move the whole envelope up and down. So congratulations, you have now designed in dual modulating vane control with variable diffusers and inlet guide vane, which regulates the airflow and optimizes the efficiency based on ambient fluctuations. The effect of this you can see in this diagram. You can see the efficiency on the Y axis, and you can see the airflow capacity regulation on the X axis. This is the modulating vane, dual modulating vane blower, where you can see that the efficiency stays near constant. There is a little effect if you regulate down, but it is quite neglectable. On the speed controlled blowers, you start in a not so good efficiency and you gain efficiency when you turn down. Multi-stage blowers have a little more limitation on the turn down, and you can see also a drop in efficiency. Screw blowers and PD blowers you can also see here. But if we're just focusing on the two types of single-stage centrifugal blowers and compare them, there is around an 8 to 10 percentage point difference in efficiency. Solely by the way the blower is regulating the airflow. No other impact, solely this. Now, we have covered the efficiency by airflow regulation. And now I would also like to cover the efficiency impact by customized versus off-the-shelf products. What I mean by off-the-shelf product and customized products is that if a client comes to a blower manufacturer and says, I need 8,200 cubic meters of air at 650 millibar at 55 degrees in the desert. Next turbo with a customized approach would design the blower geometry, the impeller geometry and the dimensions, including the gears, according to this requirement. So this blower would make 8,200 cubic meters at 650 millibar. If we look at the off-the-shelf concept, the manufacturer would look, what is the closest blower, standard blower frame size that I have that satisfies the client's requirement? For example, that could be a 10,000 cubic meter blower at 800 millibar. Yeah, but you only need 8,200 at 650 millibar. So you can see there's a certain over-design, which has, of course, an effect on the efficiency. It is unfortunately very hard to quantify because it really depends how well that standard frame size is fitting your requirements. Out of experience, I would say often 2 to 5% efficiency impact. And here you can see these customized geometries of the impeller. You can see here different manufacturing stages. And we are designing each impeller based on the customer's requirement. But the customer, of course, needs to know what he wants. He needs to know how much pressure he needs to generate and how much airflow he needs, because we are customizing the product to this requirement. If the customer is unsure about it, then there's, of course, an advantage of having a little correction knob at the blower. Now, I've touched the efficiency by regulation. I touched the efficiency by customized versus off the shelf. And I would also like to touch the efficiency by component. That is most likely the most often topic that is discussed. Not that it really makes sense to discuss it in such a high priority. As you can see, the component difference in efficiency is dwarfed by the impact that the capacity control has. What I mean by that is that if you look at the drive motor, the integrally geared uses standard asynchronous motors according to IEC rating. We have an IE2, an IE3, or an IE4 motor rating. Let's just use an IE3 with 96% efficiency. The speed-controlled blowers have a special permanent magnet motor, which is usually comparable with IE4 with 97% efficiency. There is differences. So the delta in this component is maybe between 0 and 1% in efficiency. If we look at the bearing, and we assume that an airfoil has a near 100% efficiency, no losses. If we assume that a magnetic bearing with its controller, which uses, of course, energy to lift the rotor and keep it stable, let's assume it has a 99% efficiency. Let's look at the ceramic bearings and at the hydrodynamic bearings, which have between 96 and 98% efficiency. The delta is between 2 and 3% on this component. Let's go one step down. Look at the VFD. Normally, we would compare the VFD with the gears, but the gears are already considered in these losses here. So the speed control need a VFD, typical efficiency 97%. So we have a 3% balancing difference in efficiency. There's something called a total harmonic distortion filter, which is an electrical filter, which we will touch a little bit later. There's also an efficiency impact. Now we have the impeller design, customized versus off the shelf, and of course the capacity control. And you can see that on the total efficiency difference between those two blower types, 8 to 10% you are missing if you utilize a simple speed regulation. If you put a VFD on an centrifugal air blower. Now, I mentioned total harmonic distortion. it's a little dangerous, an increasing risk that is often overlooked. Total harmonic distortion comes from a VFD. It is a distortion of the relatively smooth AC wave, the 50 or 60 hertz wave. And there is no local legislation in a lot of countries, but there is an international recommendation, the IEE 519. That's a recommended practice to approach harmonic distortion. And what this IEE 519 is saying is that the total harmonic distortion level should be below 5 or 3%. First of all, what is the danger? What is the real-life danger of a high total harmonic distortion in your local power grid? What it does is it disturbs the wave, as we discussed, which has an effect of cable overheating. It has an effect on electrical motors on your grid. They heat up more. Lifetime goes down. There can be a malfunction of the control system. You are disturbing your measurements, the measurement equipment on your local grid, etc., etc. There are ways of combating these total harmonic distortions, and this is due to with electrical filters that are making the AC smooth again, the AC curve smooth again. You have different ways. You can use a DC choke, which gets your THD level below 35. You can use a passive harmonic distortion filter, an active or an pulse width converter. So there is different price levels adjusted to it. You can see that there is energy losses on those filters. Some of those have a bypass that if they break down, you can still operate your blower, and some do not. So if the total harmonic distortion filter goes down, also your blower goes down. And as you can see here, there are some images of blowers and the corresponding total harmonic distortion filter. It has a size, it has a footprint, and it has a cost. So the key takeaways about efficiency is that a VFD is a simple way of regulating airflow on a centrifugal air blower, but it is not the most efficient one. There are better ways of regulating the airflow on an air blower other than utilizing a VFD. This is a constant speed blower with modulating vanes for airflow regulation. The result of this is 40 to 100% pressure constant airflow regulation and best efficiency over the whole regulation range. The next comparison criteria is, of course, the wide regulation range. And I still owe you an explanation why that is so important. I talked a lot about an airflow regulation range. The importance lies in the wastewater treatment process that is underlying the blower operation. We have typical load changes in a plant, which goes from between 1 to 3 to tanker plants to 1 to 8, with some certain level of industrial input. So that's the load changes in the wastewater treatment plant. The problem is that if you are on your low load and the blower gives the appropriate low amount of air into the basin, the oxygen transfer rate of your diffusers goes up. So you need even less air. And that results often that you need an airflow regulation 1 to 10. And regulation range from 1 to 10, which means 10% to 100%. Now, as you can see on the right side, with a speed-controlled blower, the VFD blower, where you have 75 to 100% regulation range for each individual blower, to satisfy a 1 to 10 airflow regulation range, you need at least 8 blower, plus 2 spare. So you are on 10 or 12 blowers to satisfy the need of the wastewater treatment plant. If you have a 40 to 100% regulation range, you can cut that down by half. So you have the options of utilizing 4 blowers instead of 8. You gain flexibility. And if you're utilizing only 4 blowers instead of 8, you have less infrastructure costs, the pipe, the energy infrastructure, transformer power, etc., civil work, less foundations, less blower room. So you have flexibility in your design. You can evaluate if less blowers is economically better than larger blowers. But for that, you need regulation range. If you over-aerate, then of course you have serious problems on your denitrification, as is explained here in the last 3 bullets. That was the second criteria. And an equally important criteria is the comparison in component lifetime. A cheap price of a blower doesn't count for much if you need to replace it 1, 2, or 3 times in the lifetime of the plant. If you have alternative with a longer lifetime, it is economically also smarter. Now, we're looking again at the Middle East region. We're looking at the Gulf region. We're looking at the environmental temperature, the climate in this area, which is 45 degrees minimum Egypt, and you should normally count on 55 in the Gulf region. If we are close to the ocean, we have a saline and salty environment. We have relative humidities, which can be quite high. And of course, we have the desert with the necessary dusty environment. We also have H2S. That is predominantly on every wastewater treatment plant, and it is very corrosive for electronics. Now, why I've mentioned the climate, the predominating climate is here, that if we look again at those 2 blower types, where we made the split according to those configurations, you can see that one type is utilizing mainly mechanical parts. We have the gears. We have the modulating vane, which is a mechanical part. We have mechanical bearings. And on the right side, you have more a focus on electronical parts. You have the VFD, you have the magnetic controller, which controls the magnetic bearings. Yeah. The impact of ambient temperature on electronics, namely on the capacitors that your electronic boards are being built up, is significant. If we look here at, for example, 55 degrees, like it is predominant in Saudi and in the Gulf region, and we look at 100% load on an electronic board, on the capacitors, then we have a lifetime of 20,000 hours for a VFD, for a magnetic bearing, as the underlying magnetic controller. Now, of course, you don't have 55 degrees permanently in this region, so you need, of course, to look at the overall temperature over the whole year. But we're also not looking necessarily at the ambient temperature, but we're looking at the temperature at the electronic board where the capacitor is built in. So without a water cooling, you will not have 55 degrees on the board. You will have a higher degree there. Now, this is just found on the internet by a simple Google search on the lifetime of VFDs from the manufacturers. So in the Middle East region, 5 to 10 years for a VFD is an ambitious lifetime. It is a theoretical lifetime, as the VFD manufacturers are stating. No? The Middle East is not a good country to run VFDs in, especially not high-frequency VFDs that are an essential part of those speed-regulated high-speed blowers. That is the reason why our magnetic bearing is not actively promoted in the region. Another reason is that electronics don't like corrosive air. They don't like polluted air. They like a clean room environment. And unfortunately, on a wastewater treatment plant, that is not what we have. If we're looking at an example here from one of the direct drive manufacturers who states the required air quality to use the blowers in, we can see an H2S content, hydrogen sulfur content of 0.5 milligram per cubic meter. Now, what does that mean? That means 0.36 parts per million. Under 1 part per million in H2S. That is something that is present on the majority of the wastewater treatment plants. Now, mechanical equipment usually allows for up to 10 parts per million of H2S. Of course, we have electronic parts on a mechanical blower as well. Nowadays, everything runs on a PLC. We have the HMI, the display. So, of course, there are some parts which are also affected by a corrosive environment. If you have an underground wastewater treatment plants, which also more and more are built around the world, H2S becomes a significant issue to handle. Now, if we look at the overall lifetime of those equipment, as I mentioned, 5 to 8 years would be my guess for a VFD in the Middle East Gulf environment. Magnetic controller, 3 to 5 years, as it's a more heavily used electronic component. But again, here, let it be 5 to 8 years. This figure is the author's interpretation. Overall, we can say that the speed control, the electronic blowers, have a lifetime of around 10 years, lower than 10 years. And on the mechanical blowers, we are looking at 25 plus years. There are examples in the market where we have 35 years and still going strong. Maintenance. It's another criteria that we need to compare the blowers against. It's an important criteria as well. But I also would like to highlight that there are two philosophies in maintenance. There is, of course, the repair versus replace. You can see the two comics here, which shows a little bit exaggerated the two approaches. On one side, you have life-extending service. You can take a part out, you can make service on it, and you have increased the lifetime of that part, and you put it back in to the equipment. You can take another piece of equipment out, you can have a look at it, you can investigate it, and you can assess how long that part will last. That gives you planning security. You can prepare for when it will fail. On the other side, you have black boxes. It doesn't allow you any service. And if we are looking at these keywords, economical, sustainable, but also keywords like the equipment needs to be available, and I would like to have a foreseeable planning with that equipment, then of course, service is a good thing. And this is, I think, also the key message of that slide here, of this presentation section. Service is a good thing. It shouldn't cost a lot, but you should have the possibility to do service on your equipment because it increased the lifetime. Now, a few examples of what I meant with life extending services and remaining life assessment. If we look, for example, at a mechanical bearing, this is now the example of a tilting pad hydrodynamic bearing. You can open your blower, you can look at the bearing, and you see a certain wear on the part. Now you can assess it and can say, okay, with this wear, it has already run for 60,000 hours. I think I can run 10,000, 20,000 hours more. Yeah, but of course I need to plan for it, and I need to buy a spare part, put it on stock, and schedule a replacement before the 20,000 hours is over. On the other side, if you have mainly electronic components, you basically have a little computer. And by looking at the board on the circuit board, you will not be able to assess the remaining lifetime of this piece. There are, of course, statistical values you can use, but of course that is again a replace over repair philosophy that has nothing to do with condition-based monitoring, because you cannot assess the condition of that part. And just by looking at the speed-controlled blowers, the VFD is a special high-speed VFD, and you have potentially also a magnetic controller. And those parts make up a big chunk of the value of the blower. If these parts go down, if these parts break down, your blower cannot operate. And it can catch you off guard. There's no way of foreseeing this by inspecting your blower. You come in the morning in the wastewater treatment plant and the blower is down. Now, you have the spare parts on stock, great. Yeah, can you repair it in the country? Etc., etc. So there is a little bit of consequences attached to it. Now, if you look at blowers, you can also see if they are made for service or not. You need to be able to go into the acoustic enclosure if you want to make service. So do you have a door? Do you have an inspection window? We can look inside. Is there space inside to assess the lifetime of some parts? Do you have mechanical instruments? Or do you solely rely on transmitters or switches? No? This is an indication that the blower is made to be able to service. On the contrary, you can also have quite a crowded environment. Everything is packed in, everything is sound isolated. Yeah? It's very difficult to do service on. These blowers are not designed to do service on. You can have a closed panel, a black box that you cannot open, etc. That should give you a little indication again if you have a black box or if you have a serviceable blower. I mentioned that service is important, but service should not cost the world. Preferable, you should be able, if you want to do the service by your own plant personnel, as much as you can. You shouldn't fly in or drive in expensive specialists. We in Next Turbo have designed the blower with ease of maintenance in mind. And just to give you a little example, it's really just picked one example out of the whole construction of the blower. There is a service A that we are recommending, and it should be done for every blower actually, because there's a lot of air going through the blower, so you should clean the air path from time to time, which means you open the volute and you just basically clean the impeller and you clean the airways in it, because despite inlet filters, you do have a lot of dust that are accumulating in the dead spaces, so you should clean those. Some integrally geared centrifugal blowers have the diffuser vane behind the impeller, which means the impeller is overlapping the diffuser vane, which means you cannot clean the diffuser mechanism behind this diffuser plate without dismounting the impeller from the shaft. And if you dismount an impeller from a shaft, which normally turns at 10 to 40,000 RPM, you need to know what you're doing in reassembling it. which means you need a specialist. Next Turbo has not designed the impeller overhanging this diffuser plate so that you can leave the rotating parts alone and you can simply do the service on the diffuser plate on the air path. Of course, we have local service in the country. If your plant people don't want to do it, you have local service providers which can do it for you. Just a simple example, which should illustrate a little bit what I mean by ease of maintenance. There are some other examples which I will, due to time constraints, now not go in. I rather want to focus on the comparison, the next criteria, the comparison in reliability and in quality. What I mean by that is operational reliability of a blower. Let's look at the 3 bearing types that we have in the single-stage centrifugal world. We have the airfoil bearing, which means, you can see it here on the right side, which means your shaft and your impeller is lifted by air. You have an air cushion that is lifting the shaft and keeping the shaft centered. For that, you need an IP23 motor. You need to be able to get ambient air into the motor because, again, it runs on air. H2S, sand, dust is not a very good thing to have, so you need to extensively filtrate the air that is in the surrounding of the blower. Air as a bearing medium, which keeps the shaft centered, has a limited shock absorption characteristic, which means if you get process-related shocks, the bearings have a function to dampen these shocks. But if you have air as the bearing medium, you have a limited shock absorption. Due to the fact that also the lifting characteristic of air is limited, usually these blowers are limited to 355 kilowatt. Now, of course, some of you might mention that there are 700, 800 kilowatt blowers in the market running on airfoil. That's true, but it's basically 2 airfoil blowers in one enclosure. It's called a dual blower. It's basically 2 air ends, 2 completely independent blower running on the same in the same package. Now the problem is, if you enter into a surge event on those blowers, you often face catastrophic failures. So these blowers should never go into surge. If we look at magnetic bearings, the impeller and the shaft is being lifted by magnetic fields, and these fields are actively adjusting around 10,000 times per second. They take the position of the shaft and regulating the magnetic field to keep it centered. So it's an active bearing. You actively interfere. That gives you a little bit more control, of course, on the shaft, on the shock absorption. Micro power outages are an issue. Usually the motor is acting as a generator. So if the power is outage, the rotating shaft generates power in order to keep the magnetic bearings also in a power outage lifted, and so that it can run down safely. Still, there is touchdown bearings, or there should be touchdown bearings in these blowers, because this generator cannot create enough power. If they are rotating down, you still have a few remaining RPM where the whole blower will fall back on the touchdown blowers. But for this, you need, of course, the magnetic controller that I mentioned, which is a small computer built into the blower. And the third is the oil bearings, ball bearings, hydrodynamic bearings. There's 2 different ways of it. Yeah, oil has a very good shock absorption and vibrating dampening characteristic. But of course, it is a lubrication oil, and that would need to be changed every 5 years. So you can see from top to bottom, we have an increasing operational reliability. Airfoil bearings more on the lower end, it's a passive bearing. Magnetic bearing is an active bearing, but you need power, you need electronic boards for it. And oil bearings on the upper end, having the best shock absorption, lifting, and also cooling capability. But of course, it requires oil change. I will jump a little bit over this topic here, and we'll move on due to time to the next point, which is the final comparison. We have looked at several criteria. We have also defined an ideal blower if it comes to efficiency, serviceability, and operational reliance. And this is my take on trying to rank these two distinct types, if you want to say so, three distinct types. Integrally geared, which is the modulating vane blower, and the speed regulated direct drive airfoil or magnetic bearing. Please keep in mind, this ranking is limited to the Middle East with its unique ambient condition. Now, if we look at lifetime, the ranking here goes towards the integrally geared with 25 plus years. On the speed drive, you have a limitation under 10 years due to the electronic parts, increased electronic parts. Efficiency, the integrally geared, same thing. The top tier position goes to the integrally geared in terms of efficiency and regulation range. As with simple speed controlled blowers, you need a trade-off between those two. Efficiency or regulation range, you cannot have both. If we look at maintenance, the airfoil needs the least maintenance, but I also have to highlight that you cannot even do service on it. You know? So yes, it has no service due to the fact that you can't do service. Quality and reliability, you can see the ranking here again. Blower price, there is again airfoil bearings, the cheaper alternative in the market, followed by magnetic bearings, and then integrally geared as the more expensive blower choice. If you look at initial capex, if you look in life cycle cost evaluation, it depends on your lifetime scope, of course. If you look at 10 years, it would still be number one. If you look at 25 years, there is no doubt that it is number one. If you need to replace your 10-year blower twice in that period, you can count on that the life cycle costs are shifting towards the integrally geared. That is my take on ranking the blowers. Of course, that ranking also depends on the individual project requirements, project surroundings, project criteria, and also who is looking at it. Is it an EPC? Is it an end user? Is it an operating company? Now we have compared the field of blower equipment. Now I would like to show some practical best practices. I wanted to show you what else Next Turbo can offer, not just the blower equipment, but also give you some practical hints, some practical guidelines that you can use in your daily professional life. This is an example of a replacement of a PD blower in Jebel Ali. PD blowers in the Gulf region and the Middle East region, we can see an increase in demand of replacing these lower efficient equipment with single stage machines. There's more and more examples. That's a trend which seems to be happening in the Middle Eastern region. You can see here in this example, we had 10 PD blowers divided in two lines. There were two aeration lines with 4+1 each, so 10 in total. with a 500 kilowatt drive power and an external VFD in an air-conditioned room. We replaced those 4+1 blowers with 3+1 blowers. So out of 10 blowers, we made 8 blowers, again with 500 kilowatt. We reused the VFDs and we matched the airflow. So that should already indicate you the energy savings, as we have reduced the installed motor power significantly, by more than 33%. You can also see, here you see the PD blower in the background. There is a reduction in footprint. And the challenge here in that plant was, of course, that the plant was a running plant, so we had limited time to shut down an aeration line. So everything needed to be prepared and changed under running operation. If you have enough data, operational data on your plant, we can provide a case study. We can provide. There was 11 months of data available in Jebel Ali. We could use it. We could simulate the energy usage of that new blower, compare it with the old blowers, and could basically come up with a case study on energy savings, which was the prerogative for this project. We can offer a support in blower room design. The Middle East has a unique challenge, as I mentioned, the ambient condition, the temperature. So there is a few blower room and blower configurations that we would recommend. The top one being that there is a lot of heat being generated from the electrical motor, but also from the oil cooler, the cooling, whatever cooling you have in your blower system. So that's all generated within the acoustic enclosure. And it's normally discharged into the blower room. Normally you have a fan here, which just blows the hot air into the blower room. What you should make sure is that you duct this heat out of the blower room. There's no need to heat up your blower room and then install additional fans to move the hot air out. It's not good for your equipment. Why not just guide it out directly? For the oil bearings, you need an oil cooler. And that oil cooler can be placed inside the acoustic enclosure, on top of the acoustic enclosure, where it blows into the blower room, or outside. And in the Middle East and Gulf region, outside makes the most sense, because in the blower room, you usually have up to 5 degrees higher temperature. Why do you want to make your life harder with the cooling if you put it in a hot environment? So move it out, take the outside air, but of course use a canopy, put it in an elevated position so that you don't need to clean it off sand all the time. Suck in from an air channel. Next turbo allows you to adjust the discharge direction in 15 degrees intervals. You can see, due to the fact that we had a column of the blower room in the way, we did go out at a certain angle so that you have that flexibility in adjusting the blower configuration to your blower room. There is more that you can see on the right side. We don't need to discuss it. The only thing is there are some special cases where we can support you as well, and that being underground wastewater treatment plants and outdoor container solutions. And if we look at outdoor container solutions, we have provided some worldwide, but also into the region for outdoor placement. We have supplied some in the UAE, where you can see a containerized solution here for outdoor placement with the blower inside, every equipment inside. You just need to straight dump it outside and have a running solution. I also often get the discussion with EPCs and clients on the motor starter, the motor voltage. And of course, with integrally geared modular vane blowers, not the high-speed speed-controlled blowers, but with the integrally geared type blower, you have the advantage that you can choose a medium voltage motor as the drive motor. That gives you an advantage. You can reduce your transformer capacity, going down from medium voltage to 400 volt. You can reduce dramatically. And if you imagine that you have 10, 12 blowers with 500 kilowatt each, that is an enormous amount of megawatt in transformer power that you would need to provide, that you can save. If we look at starter choices, motor starter choices, we have, of course, the VFD. The point is a VFD sometimes has bypass, sometimes don't have bypass. If you only use it for starting the motor and then you don't use it at all anymore, it's a waste of energy. Of course, sometimes it might be required if you have a very weak power grid, where you need the motor to start very, very slowly. What I would always recommend is a soft start. If the initial starting current of the motor is too high, then you can deploy a soft start and reduce the starting current by usually 50%. Or a direct online, which normally results in around 7 times the nominal current during start. If you have medium voltage motors, direct online is the choice that is almost always used, as these medium voltage motors already have a 50% reduced starting current. So you normally have only 3 times the nominal current during start. So it can save you in infrastructure, transformer power, and it depends, of course, on what voltage you are getting in. If I'm talking medium voltage, I'm talking 3, 3.3, 6, 6.6, 9, 10, 11 kilovolt. This is the presentation. I covered the world of centrifugal single-stage compressors a little bit. I've seen that there were some questions already being written down in the chat. So I would definitely go to the question and answer session. If you have any questions, please shout out. I will have a look at the chat as well. Maybe Maha and Heidi, you can support me here a little bit if the question is written in Arabic.
Yeah, sure.
Yeah, sure.
Here we go.
Okay, so feel free to send your questions in the chat box and Mr. Florian will answer them.
Just going through the chat. I can see one question. The second part of the, oh, sorry, there was one. Yes, there was one question on the capex of the integrally geared modulating vane blowers compared with the turbo blowers. Yeah, working on VFD. There was a question on the capex. Where's the capex difference? Yeah. As I said, it depends a little bit. If it's an airfoil bearing or a magnetic bearing, there's a price difference. Magnetic bearing is usually a little bit more expensive. It depends also heavily on the size. For example, you have a total air requirement of, let's say, 100,000 cubic meters. Usually, the turbos would split that down, as I mentioned, to 10 turbos. But the integrally geared would choose larger blower sizes and less of them. So you maybe have 4 blowers, 4 larger blowers. So the question is, if you compare this, then the integrally geared can be lower or same price as the turbos. If you compare a 500 kilowatt machine of the integrally geared with a 500 kilowatt of a magnetic bearing, then of course the magnetic bearing is cheaper. Yeah. So I hope I've answered that question a little bit. It depends on what scope you are looking, your whole project or a one-to-one blower comparison. There was a second part to this question, and it was, if all these moving parts, do they need maintenance? And as I mentioned, yes, they need maintenance. Maintenance is a good thing if you can do it on site. If you have plant personnel and the service is as easy so that your plant personnel can just integrate it in their usually maintenance scheme and can fulfill those. If you need to call in foreign experts or experts from the manufacturer, it can also be local experts, that costs money. That makes the service unnecessarily expensive. Let me see if we find another question. Heidi, if you see some, please feel free to read them out to me.
Yeah, someone is asking, do you must maintain each 2 years?
No, you don't need to do maintenance every 2 years. We are recommending, and I think in the Middle East region, it makes sense to clean the air path around every 3 to 4 years. I would recommend to do that on every blower, independent if it's a turbo or if it's an integrally geared. I would recommend that on all. On the turbos, unfortunately, you can't because you cannot open them and clean them. But on an integrally geared, I would recommend to do that every 3 years, every 4 years. You can do that the first time after 3 to 4 years. Have a look in it. If everything is in order, you can extend that interval. If it is very dirty, maybe you need to shrink that interval.
Yeah, okay. Someone is asking, I prefer to use VFD instead of soft start. VFD need AC, but a lot of electrical engineers request soft start. What are your opinion?
Yes. This exactly. I think I touched a little bit this question in one of the slides. If you don't use the VFD for speed control, if you don't regulate your capacity with a VFD, which we established is not a very good idea to do, you only need the VFD for motor starting. I think it's not a good idea to use VFD. A soft start is normally the better choice. You use it to start the motor, and then it's automatically bypassed. The motor is started, the soft starter, boom, has no additional losses. A VFD, you often have losses even after the starting, and then you just run the power through the VFD for no reason. If you have a bypass on a VFD, that's another issue. But of course, a VFD also costs more than a soft start.
Okay, the next question.
Please.
Could you give me a hint about the adjustable impeller blades, or what's called the modulated van, as I couldn't imagine how is it and it operates. Interested in understanding the mechanism that allows the blades to change angle and how this modulation affects airflow efficiency and performance.
Yes, exactly. This we touched a little bit in this section here, where you can see that let me start the video again, that by changing the angle of those vanes, you are basically moving the compressor curves along the airflow range. In other words, let me use some other words. Maybe it gets a little bit clearer. You change the airflow by changing the speed of the air. Yeah? So you need to change the speed of the air to change the airflow. You can do that by changing with a VFD the speed of the impeller. But the speed of the impeller generates the pressure. So by doing this, you have at the same time a pressure drop when you regulate the airflow. What we are doing is the pressure generating speed on the impeller, we leave constant, which means if the speed here is constant, the pressure is constant. And we change the airspeed by changing the angle and therefore the relative airspeed after the impeller. So pressure is generated here and airflow is regulated here. You have decoupled the airflow effect and the pressure effect. You have decoupled it. You have a two-point control, we call it, or a dual point control. You are operating the pressure independent from the flow and vice versa. So that's in other words explained. And the summary of the effect on efficiency is 8 to 10%, where these vanes are more efficient than a VFD speed controlled. Yeah.
Yeah.
We can have a more in-depth talk about it, where we can go a little bit more into the specific effects that we use one example and show you the effect on airflow, efficiency, performance, etc., etc. Now, is there a rule of thumb for selecting air blower type regarding the capacity and pressure? It's a very good question. If I may jump to the field overview of the blowers. The volumetric machines, the PD blowers, the volumetric part of it, I would recommend below 50 kilowatt, below 1,000 cubic meters. You can choose the lobe blowers. If you go higher in airflow, larger in plant size, you would need to take single stage. Now, you can argue when to use a speed regulated and when to use a variable vane machine. And the question is between 0 and 500 kilowatt. The question is not so much the size of the airflow or the size of the blower, when to choose which. It is, do you have a target to reduce energy consumption, yes or no? Do you have a target where you are responsible for this equipment more than 8 years? If you answer, yes, I'm responsible for this equipment more than 8 years, I have the budget, and I'm responsible for the energy bill, then you should always, independent of size, choose a variable vane blower. If your budget is limited, your initial CapEx budget, then of course you can choose a speed regulated machine. Now, if we are talking about over 400 kilowatt blowers, I would never use a speed controlled machine. Over 400 kilowatt, as I mentioned, the airfoil bearing machines over 400 kilowatt is usually a two-stage machine. Sorry, two-stage is wrong. A dual machine blower, which means it has two blowers in one enclosure. So to me, it's not one blower, it is still two blowers. One question was if we could share the data sheet of it along with the product list, and I think we will be able to do that. We will address that after the meeting. There is one saying that I think the pressure also will decrease.
Data sheets will be sent on the group.
Please, Heidi.
Yeah, sorry.
Yes. There was one additional question. There was one question that I think the pressure also will decrease. If we look at, I think this is comparing to the modulating vane, where I said that by changing the angle of the diffuser, I said that the pressure will not be affected, only the airflow. And of course, the person who says that he thinks the pressure will also be decreasing is of course correct. The effect here is very much simplified. What will happen in reality is that if I change the angle, if I change it to 80%, actually the pressure will increase a little bit. So this curve will be a little bit higher, and then it will decrease a little bit. Yeah. So you have basically such a camel-shaped top curve. So yes, you are right. It will decrease, but only slightly. There's another question of how does it operate? And if I may jump to those two devices here, the variable diffuser vanes and the inlet guide vanes. And I think the question is referring to who is changing, who is deciding when to change the angle. And the question is the blower itself. The blower has a local control panel, a PLC-based local control panel, where it looks at the ambient temperature, it looks at the pressure, it looks at the required airflow from the SCADA system or from any pressure sensor or any other sensor. And depending on those readings, it ensures that the inlet guide vane and the variable diffuser vane are in the needed and most optimum position. So those two blades are automatically being adjusted by the blower itself. There's another question which refers to if these blowers work together with surface aerators, and the answer is no. These blowers are used for bottom diffusers. Of course, we can provide the air for a surface aerator, but if you already have high efficient blowers, you could theoretically also use a bottom diffuser aeration system. But again, we can talk about that a little bit later after the meeting.
Okay.
We can come back to that. Please. Yes, I'm just looking. Yes, there was one question. I didn't understand what 800 hertz besides the VFD refers to. And that is a very fair question. Let me just see if I find the slide. Yes, I think he's referring to this slide here. The 800 hertz, what I'm meaning by that is that the speed controlled blowers, the turbos, you cannot just buy a VFD around the corner, a normal 50 hertz or 60 hertz blower. What you need is you need to get the motor speed, the speed of your motor, which normally runs at 3000 RPM at 50 hertz. You need to get that to around 10 to 40,000 RPM. So you need a high frequency VFD. It's a specialized VFD. It's not a standard 50 to 60 hertz VFD that you use on PD blowers, on pumps, or on anything else. It's a very specialized high speed, high frequency VFD. You need this to get the motor up to speed. That's why this VFD is operating 500 hertz, 600 hertz, 800 hertz, not 50 to 60 hertz. Another question is, what about using AI to control the blower speed or to protect the blower from unexpected operational problems? Now, AI is a very big buzzword, and surely there are applications to this. An AI will not help you in the speed control of a blower to overcome the built-in thermodynamical problem or physical problem that you have of the pressure drop. It doesn't matter how you change the speed of the blower, you will always have this pressure drop. That's a built-in characteristic of the physics of compressing a compressible gas. You're not getting around the pressure drop that you're having. Yes, there's one question. As you mentioned, the temperature and humidity are very high in the Middle East. What solution does your company offer to address the corrosion problem? The blowers, integrally geared blowers that we are offering, they can run, for example, against 10 parts per million H2S. It's a very high concentration already of H2S. The mechanical parts of the machine are not affected by it. What is affected by the H2S, of course, is the local control panel, you know, the PLC and the electronic, the brain a little bit, yeah, the control system. Now, what you can do there is you can, for example, suck the air, the cooling air for those electronics. You can suck that from a position where the H2S content is lower, which means by a chimney, or you have a ducting which gets it from another part of the plant, and then you use this air to cool the local control panel. You can move the local control panel as well into an air-conditioned room. A local control panel is not a power part, it's the brain, it's a PLC, so it doesn't need so much air, which means you don't need so much energy to air condition this panel. You can also build in a small little air conditioning into the local control panel, which stands next to the blower itself. So the blower itself doesn't really care how hot it is. You can get it into 60 degrees environment. The blower itself doesn't care. We can choose the instruments that they can sustain 80 degrees. The blower itself doesn't care. Only the electronics. Yeah, there's another question, and I think I already answered it, how we can control the angle of these devices by changing the flow, and does this control change over time? And the brain behind these two modulating vane systems work together. That's, of course, there's a lot of brain power behind it. And that's, of course, built into the local control panel so that they work best together. And they are dynamic. So they change automatically over time. What I mean by that is, in winter, you have a different behavior of those vanes than you have in summer. During night, you have a different behavior than what you have during the day. You know? So they are already depending on external instrumentation. Yes. Okay. There's a question for volumetric positive displacement blower types. What are the alternatives for flow control? If I jump back to the overview over the compressor field, yep. We're talking about those lobe blowers and how you can change the airflow. With this type, the only chance you have is a VFD. So a PD blower, there's no alternative. The working principle is also different to the centrifugal. So a VFD doesn't have these issues that it has on the centrifugal machines than it has on the PD blowers, because the PD blowers are grabbing a volume of air and moving it to the pressure side and releasing it to the pressure side. So if you need more air, you basically do that quicker. That grabbing the volume and releasing it, you're just doing quicker by having a VFD, which makes the lobe turn quicker. No? So it is a different working principle. Which part is responsible for changing the angle of those diffuser vanes? Is it mechanical, electrical, or an actuator? And you are referring to those mechanisms here, those diffuser vanes and those IGVs. And the answer is it's an actuator. It's a linear motor. I will be able to show it to you on those pictures here. You can see here, I don't know if you can see my mouse. Let me just go to the laser pointer. You can see here, that is the linear actuator. So that's the actuator. That's the diffuser arm, where you can see here the position, the mechanical positions with a limit stop, and a linear actuator, which by moving this arm, you move the angles of all those diffuser vanes simultaneously. I'm jumping a little bit over the questions where I don't have an immediate answer, as I'm not an electrical engineer, I'm a mechanical engineer. So some questions I have to jump over.
Okay, Mr. Florian, regarding the Arabic question, which type of blowers have a longer lifespan and produce less noise?
Yes. Good. I think the lifespan I've touched already. Let me jump to the slide. The lifetime of the speed-controlled blowers is usually below 10 years. I would say around 8 years you have these VFD-controlled blowers. A lifetime in the Middle East, around 8 years, plus minus. Some last a little bit longer, some last a little bit less. It really depends. But the fundamental issue is the lifetime of the VFD and of the magnetic controller. And that makes up the majority of the investment costs. You have a big chunk of the blower's value that you need to replace after 5 to 8 years. The lifetime of these modulating vane blowers, which uses mainly mechanical components, is 25 plus years. So if you're thinking single stage centrifugal blowers, if you go for lifetime, it would be the modulating vane integrally geared blower type that you see here displayed at the bottom. Yes, what is the control range of the diffusers? That is one other question. And if you allow me to go to the slide, the control range of the variable diffuser is 100% to 40% of airflow at a constant pressure. Very important to add at a constant pressure. So it's a pressure constant 40 to 100% in airflow. Now the question goes further and says a VFD can reach 50%. And here I would like to jump to another slide, this one here, because this is explaining the speed control. And a VFD blower will be able to reach 50 to 100% only if you over-design this blower significantly. So if you move the design blower curve here, somewhere up here. If you over-design a speed-regulated blower significantly, which means it runs very far away from the best efficiency point, then you can have 50 to 100% pressure constant again. If you are talking not pressure constant, then of course we can turn down the speed even further, and then we have a curve which is here. And then of course from here to here, you can have a 50% turn down, but not pressure constant without over-designing the blower. No? So 50% regulation range on a VFD, not pressure constant, or by having a very, very bad efficiency. Let me see if we find some more questions. If you have,
someone is asking.
Please, if you have some, feel free to post them.
Yeah, someone is asking what the control range of diffusers, for example, VFD can reach 50%.
Exactly. This is what I just answered. Correct. That's the question I just answered.
Okay.
And if we have some more on top here. Yes.
Okay, there's a question.
Please.
these modifications are impressive, but they significantly impact the price. Customers often don't appreciate the added value and might be reluctant to buy. How do we address this?
Yeah. Yes. As I mentioned, if you look compare a 200 kilowatt blower of the turbo type, of the speed control type, with an integrally geared compressor, 200 kilowatt, the 200 kilowatt integrally geared will be more expensive. No? Out of question. There is more parts on it. It has a higher manufacturing quality. It will last 25 years. So yes, it is more expensive. But as I mentioned, often a client is interested in a total amount of air. In a wastewater treatment plant or any other project that you have, he wants 100,000 cubic meters of air. If the client leaves the option to choose the number of blowers to you, then integrally geared will be cheaper, because I will offer 4 bigger blowers where the speed controlled will offer 10 or 12 smaller blowers. And then suddenly the initial investment costs, the initial capex, will be cheaper for the integrally geared blower. If we then, on top of that, add what the EPC needs to pay more in a larger blower room, in more piping, because he has 12 blowers and not 4, electrical infrastructure, total harmonic distortion filters, air conditioning, extra filtration of the blower room because they need a more clean environment, it gets even more clear what is cheaper. No? So the focus should be not on the individual blower, 200 kilowatt versus 200 kilowatt, even if that would be the comparing scope. The question is, how long are you evaluating your blowers for? Just the initial capex? Absolutely, we're more expensive. If you look at how much capex you would need in 20 years, if you need to replace after 10 years the blower, the speed controlled blower anyhow, we're again cheaper. So it depends on the project setup, no doubt. I hope I could answer the question.
Yeah, thanks a lot.
Feel free to reach out also in the upcoming days. I will be traveling the next days in the Middle East, so my response might be a little bit delayed. But after I'm returning, I will definitely focus on your questions as well. So feel free to reach out if there's any other questions. Yeah?
Thank you very much, Florian. And we are waiting you here in Saudi Arabia and Middle East. And hopefully all the gentlemen be patient for this next couple days. And I think we covered all questions. Yeah.
Thank you.
Thank you very much, gentlemen. And see you soon in this series of best applications and the smart STBs. From my side, thank you very much.
Thank you very much. Thank you. Bye-bye.
Bye-bye.
Thanks a lot, Mr. Florian. We'd like to centrally thank all of you for attending today's webinar and for your valuable time and engagement. A special thank you to Mr. Florian for the insightful and technically rich presentation and for sharing real-world experience on next-generation turbo blower technologies and their impact on wastewater treatment plants' performance. And thank you, Dr. Maher, for joining us today. This session marks the second webinar in our Smart Wastewater Treatment Plants series. where we aim to provide a practical and comprehensive understanding of modern aeration systems from intelligent control to advanced blower and diffuser technologies. Our upcoming webinar will focus on the third essential component of aeration process in wastewater treatment plants, diffusers. We'll also feature advanced process solutions such as Chercon and Cleartech textile fixed bed, and this will be on Friday, February 13th from 4 p.m. to 6 p.m. You can join the WhatsApp group via the link sent on the chat box to stay updated. We hope today's discussion has given you clear insights into how modern blower solutions can enhance efficiency, resilience, and long-term operational sustainability in wastewater treatment plants. Thank you once again for joining us, and we look forward to welcoming you in the upcoming sessions of this series. نشكر حضراتكم جدا على حضوركم ومشاركتكم في ويبينار النهارده، ومقدرين جدا وقتكم وتفاعلكم، وشكر خاص لمستر فلوريان على العرض القيم والمحتوى الفني الغني ومشاركته وخبراته العملية في مجال تكنولوجيا التربو بلاورز الحديثة وتأثيرها المباشر على كفاءة محطات معالجة الصرف الصحي. ويبينار النهارده هو الويبينار الثاني ضمن سلسلة محطات الصرف الصحي الذكية، واللي هدفها تقديم رؤية عملية ومتكاملة عن أنظمة التهوية الحديثة بداية من التحكم الذكي ووصولا لأحدث التكنولوجيا البلاورز والديفيوزرز. الويبينار الجاي هنركز على المكون الثالث من المكونات الأساسية في عملية التهوية في محطات الصرف، وهو الديفيوزرز، وبعض التقنيات المتطورة زي تشيركون وكليرتك تكستايل فيكسد بيد. وده هيكون يوم الجمعة 13 فبراير من 4 ل 6 مساء. علشان تتابعوا كل جديد تقدروا تنضموا لجروب الواتساب من خلال اللينك المرسل في الشات بوكس. أتمنى أن الويبينار النهارده يكون وضح بشكل عملي إزاي الحلول الحديثة بتساعد المحطات على تحسين الأداء، تقليل استهلاك الطاقة، وزيادة الاعتمادية والاستدامة على المدى الطويل. شكرا لحضراتكم مرة تانية. And thanks again Dr. Maher and Mr. Florian. We have the honor to have you with us today. Thank you.
Thank you very much.